Wi-Fi is free. We already have it. Just use Wi-Fi. That assumption has delayed more IIoT projects and caused more data quality issues than any other single decision in industrial connectivity. In an industrial context, Wi-Fi is paid for in dropped messages, unreliable data, and the engineering hours spent troubleshooting connectivity that was never built for heavy industrial loads. Today, we evaluate the math behind all three physical network options: 4G LTE, Wi-Fi, and wired LAN. Every protocol has a precise application. We have to start with the physical reality of the space. Factory floors generate intense electromagnetic interference. High-voltage motors, variable frequency drives, induction heaters, all of these continuously disrupt wireless communications. Add in the physical obstructions. Concrete walls drop Wi-Fi signal strength by half. Passing through a heavy steel tank or crossing a line of active welding equipment effectively eliminates it. Attempting to route continuous, delicate sensor telemetry through an environment explicitly filled with RF shields and electromagnetic noise is a predictable engineering failure. IT departments frequently offer their corporate Wi-Fi as the IIoT backbone, but that infrastructure is designed for burst traffic, a laptop downloading a file or requesting a web page. It is not engineered to handle a continuous stream of 50 machines publishing sensor data every single second. When you force continuous IIoT traffic onto IT infrastructure, the network degrades. You see intermittent disconnections, DHCP IP address conflicts, and massive latency spikes during peak usage hours. On the factory floor, this looks identical to hardware failure. Maintenance teams end up replacing perfectly good sensors, completely unaware that the actual issue is network congestion. Industrial wireless design is a separate discipline from enterprise IT. Getting it right requires deployment-tested frameworks, not office hardware. We begin with the gold standard. Wired Ethernet is the correct answer for industrial IoT wherever you can physically run a cable. A wired connection is deterministic. It does not drop packets when a nearby motor starts up. It ignores electromagnetic interference and physical metal blockages entirely. It also provides massive bandwidth surpluses. Telemetry via MQTT for 100 machines publishing every second requires about 5 megabits per second. A standard 100 megabit line gives you 20 times the capacity you need. Security is physically enforced. There is no RF leakage to intercept, and TLS encryption secures the data over the wire. The trade-off is the initial deployment friction. Routing conduit through existing facilities requires physical penetrations, labor, and upfront capital. The rule is uncompromising. If you can run a cable, you run a cable. The reliability dividend over 5 years of continuous operation easily exceeds the initial installation cost. Look at this comparison table. Wired LAN anchors the network with 99.9% uptime and latency locked between 1 and 5 milliseconds. That is the baseline. For assets where running a cable is physically or financially impractical, outdoor infrastructure, mobile assets, or elevated structures, 4G LTE is the required alternative, not Wi-Fi. The difference comes down to spectrum. 4G LTE runs on licensed spectrum managed by a cellular carrier. It does not compete with the business applications sharing your internal corporate network. Wherever you have a cellular signal, you have a connection. You eliminate the need to plan access points, run RF surveys, or analyze local interference. Latency increases to roughly 30 to 100 milliseconds. While slower than a hardwired LAN, 100 milliseconds is imperceptible to an operator monitoring an MQTT dashboard. Updating the comparison chart to include 4G LTE reveals the data math. Because MQTT is highly efficient, 50 machines publishing 10 data points a second generate only about 96 megabytes a day. A basic industrial SIM handles that effortlessly. Using industrial gateways with dual SIM slots removes single carrier dependency. If the primary carrier goes down, the gateway automatically fails over to the secondary network. For anything geographically distributed, moving, or temporary, LTE provides a level of stability that local wireless simply cannot match. This leaves Wi-Fi. Wi-Fi can work for IIoT, but its operational window is extremely narrow, typically limited to light administrative areas or highly controlled low-density sensor deployments. Place it near heavy induction equipment or welding bays, and the packet loss spikes. Bringing Wi-Fi into the chart reveals the cost of that packet loss. A seemingly minor 2% loss rate on a 1-second publishing interval means you are missing 1,728 data points per machine every single day. When that telemetry is forced to compete with business applications for channel time, the data quality degrades precisely when the facility is busiest. If Wi-Fi is genuinely the only physical option, the deployment requires strict parameters: industrial-grade access points, high-density coverage mapping, and WPA3 enterprise security. It is the connectivity of last resort. It requires near-perfect environmental conditions to function adequately on a factory floor. This diagram outlines a hybrid architecture mapping framework. Real facilities do not use one protocol site-wide. They map the connectivity to distinct environmental zones. Zone 1 is the production floor. It is dense and high interference. All stationary machines here are strictly wired LAN. Zone 2 contains outdoor and remote assets like water tanks and substations. These map to 4G LTE using dual SIM gateways. Zone 3 covers warehouse and logistics. The lower interference here makes it suitable for industrial Wi-Fi to track mobile assets like automated guided vehicles and forklifts. Finally, Zone 4 handles temporary or construction phase monitoring. LTE nodes deploy here to avoid sinking capital into infrastructure that will eventually move. A resilient factory network evaluates each asset individually, integrating all three protocols into a deliberate, engineered mosaic. Consider a transformer failing at 2 a.m. or a burst pipe at a remote pump station. The local infrastructure failures that sever your network, like power outages in the switch room or damaged cabling, often occur during the exact events that cause the mechanical failures you need to be alerted to. True resilient design accounts for this. It means pairing your primary wired LAN gateway with an automatic cellular backup. When the primary line is cut, the gateway shifts to cellular. The MQTT connection reestablishes, buffered data replays, and the platform resumes a continuous data stream. This failover flow illustrates the timing. Activating a cold cellular SIM takes 30 to 90 seconds. A warm standby SIM that is already active drops that recovery time to under 10 seconds. Maintaining that cellular SIM in a warm standby state costs roughly 300 pesos per month per gateway. For a facility's most critical infrastructure, that negligible monthly fee is the most cost-effective operational insurance policy available. The idea that corporate Wi-Fi is a free, simple solution for the factory floor is a massive operational liability. Default to wired LAN wherever a cable can physically go. Use 4G LTE for remote or mobile assets. Restrict Wi-Fi to highly controlled edge cases, and ensure every critical asset relies on a warm cellular standby. Walk your facility this week. Audit every asset installation point and categorize it into its proper connectivity zone. That map is the foundation of your network. With the physical layer secured, our next episode moves to the data layer. We will map the strict transition from preventive scheduling to true predictive maintenance. Subscribe. Every layer of the architecture is now mapped.